So we've been building up to this moment. We've been using dynamic scheduling out-of-order execution to keep our pipeline well-utilized even in the face of read-after-write dependencies. And we've seen the importance of retaining precise state so that the processor is able to abort and restart at any instruction in case of exceptions or control misspeculation or other misspeculations. You're now an expert on the MIPS R10k implementation of out-of-order execution with precise state. And at last, we get the we're going to see how the MIPS R10k uses its reorder buffer, its physical registers, to implement precise state. In this video, we'll start with the concepts of restoring precise state, and then we'll turn to a quick example considering an alternate timeline of the example we saw in the last video, where one of the instructions suffered a page fault, it had an exception. How would the R10k recover in that situation? And then in the subsequent video, we'll have a very quick recap of this module on dynamic scheduling with speculation, with support for precise state. Now, remember how we got here. The whole problem was that Tomasulo's algorithm performs out-of-order write-back of the architectural register file. But here in the R10k, we're seeing that the physical registers are written out of order as well in the... But in contrast to Tomasulo's algorithm, this is okay. The difference is there is no architectural register file. There is no longer a primary source of storage for the registers defined in the ISA, the architectural register file. So how can we identify the precise state of the architectural registers immediately prior to some excepting instruction? Well, the idea in this design is that we can free the written registers and restore the old ones. So we will restore precise state. We will do this by manipulating the map table and the free list. Notably, we will not manipulate the register file. The data in the physical register file remains the same, but how we interpret that data using the map table and the free list, this is how we will restore precise state. Broadly, there are two ways of restoring the map table and the free list so that we can ultimately restore precise state in the MIPS R10k design. Option one is a serial rollback using the output tag, the current output tag, and the old output tag for every instruction. That is, when we need to abort and restart, either due to a discovered branch misspeculation or an exception, one by one, we restore the map table to point to t old and we free the physical register pointed to by the new output tag t. There are trade-offs in this design, so really there's a plus and a minus here. This approach is slow, it's sequential, but it's simple. And this drives down cost. Our second option is a single cycle restoration from a checkpoint or a snapshot. The idea here is to make a copy, a snapshot of the register map table and the free list at various points in time, at various instructions. And when we need to restore precise state, in a single cycle, we simply copy in the values from the relevant checkpoint. And again, we have a trade-off here. This approach is very fast, single cycle, but checkpoints are expensive. We would be spending our on-chip resources, our transistor budget, to effectively multiply the space required for the map table and free list, not to mention the additional wiring required to make this operation fast. So modern processors make a compromise between these two options. And we've seen this goal before. We should spend our resources and engineering efforts to make the common case fast. So we could spend a small amount of on-chip resources, of area, to checkpoint only the low confidence branches. And otherwise use serial recovery, option 2, for page faults and interrupts. Specifically, the goal is to use this serial recovery rarely, so we're expecting rare rollbacks. I'd like you to think a little more about this compromise. Given some fixed number of map table and free list checkpoints, why wouldn't we dedicate a checkpoint to make a snapshot at every instruction to support interrupts and exceptions quickly? And why would we only dedicate checkpoints to some branches and not others? Great, so those are the key concepts of how to restore precise state in the MIPS R10k. So let's put that serial rollback into action, and we're going to jump over into an example, taking an alternate timeline from the example in the last video. So let's return to the problem that motivated this entire module, a page fault in that first store instruction. Now, our goal is to abort the accepting instruction, deal with the exception, that is, run the page fault handler, and restart execution starting from the store. Tomasulo's algorithm wasn't able to do that due to out-of-order writeback, but in this example, we'll see how the R10k restores precise state using serial rollback. So the data structures we have in front of us are a snapshot from cycle 19 in our example from the last video. We're in the retire stage, and we've discovered that the store hit an exception, a page fault, say during the execute stage or the complete stage, the address computation, and we've discovered a TLB miss. Now, I don't cover virtual memory in this course, as it's covered in ECE 344, but if you're curious about the very useful feature of virtual memory, our textbook dedicates some content to that concept. Okay, so we're in the retire stage, cycle 19. We need to handle this exception. We need to make it appear that all instructions before the store have completed atomically, and that the store and all of the subsequent instructions have not even begun their processing. Those are the sequential semantics. Now, the problem is that the subtract, the branch, and the load instruction, they have completed, meaning that they updated the map table and they allocated physical registers from the free list. But since these instructions have not retired, we have in-order retirement, we are able to roll back their register mappings and their changes to the free list. And that's what we're going to do in this example. So come along with me. We start the serial rollback at the tail instruction, at the youngest instruction in the instruction window, and we want to undo all of its effects, the sub-I instruction. So what has that instruction done? Well, it allocated a reservation station, it allocated a physical register for its output, it updated the map table, and it allocated an ROB entry, and we're going to undo all of those effects. We free the reservation station entry, we free the newly allocated physical register, and we return it to the free list. We restore the map table, indexed by the name R1, to its previous physical register, and we free the reorder buffer entry, since we're now done undoing this instruction. Great, that's step one. Step two, we start at the tail again, and we're going to undo this store instruction. Since the store has no output register, we don't need to change the map table or the free list here, but we free the reservation station entry and the ROB entry by moving the tail pointer upward again, or in this case, all the way around. It's a circular buffer. That's step two. Step three, hopefully you're seeing a pattern in this serial rollback. We start at the tail and we're undoing the multiply instruction. So we free the newly allocated output register, physical register number 1, sending it back to the free list, and we restore the map table for that output register name F4 to the physical register that used to represent F4. In this case, we don't free the reservation station entry, since we can inspect the instruction status bits, and we see that the multiply finished its execution, so it already freed its reservation station entry. This is another purpose of tracking the instruction status over the course of processing. And finally, we free the ROB entry, since we've undone this instruction, so we move the tail pointer upward. We undo the tail instruction again, this time the load, freeing its allocated output physical register, and restoring the map table for F0, its output, to the previous physical register. And we free the reorder buffer by moving the tail pointer upward. As we've seen before, this instruction finished its execute, so there's no reservation station entry to free. On to the next. You're getting the idea. I'll skip over the branch instruction, but it had no output tags, so nothing to change in the map table or free list. So now our tail instruction is at the subtract instruction, and that should say sub-I. You got the idea. We free the newly allocated physical register, return to the free list, and restore the map table entry for register name R1 to the previous physical register, which is number 4. And at last, the head pointer meets the tail pointer. This implies that the effects of all of the younger instructions have been undone. So indeed, the map table represents the values for all of these registers, F0, F2, F4, as they should be seen at the precise state that the store instruction would start its processing. Now, this quick example went over the recovery for register updates, but precise state also concerns the state in memory, and this is exactly why store instructions do not update memory until they retire. So even this store instruction, which suffered a page fault, it has yet to update memory. I will wrap up this video here. At long last, you've seen what we've been working toward, the ability to abort and restart so that we retain correct sequential semantics for exceptions, but this also applies to control misspeculation. If, say, we opt for a processor design that uses serial recovery for some branches, then when a branch misprediction or BTB misprediction is discovered, say in the execute stage or in the complete stage, depending on how aggressive your pipeline is, then we would use the same recovery procedure to roll back all younger instructions than the misspeculated branch. There are other design trade-offs we could make with branches. We could also perform the recovery to precise state when a branch retires. So that's it. I will see you in the next video for a very brief summary of the MIPS R10k and dynamic scheduling with speculation more broadly. So I'll see you there.